welcome all back. We have now seen first order equations, and our next topic will be, yes, second order equations. But before we do that, we want to do at least see a couple of applications, because the intent of this course is, on one hand, to give an introduction to differential equations and to at least be able to solve the most common and the most frequent ones, but also to convince you that they're the most common and frequent ones by showing how they are occur in nature or how they are used in other sciences. And we have already discussed one such thing briefly. I think I did actually really discuss it in the homework session video of population growth. And but there's another. When we talked about population growth, we also have this 4.1 is about growth and decay, but I'm going to go very quickly over that because that is not really differential equations yet, and I'm sure most of you, no, actually everybody of you has seen this in other courses before, in 1275, 1375, or whatever pre-calculus courses you have taken elsewhere. And so I don't want to spend too much time on that. And the second one is again from physics, cooling and mixing. And we will also see some applications later on. What's the last topic? Sorry, I'm blanking out now. Element mechanics. Okay, so let's jump in here. So what about growth and decay? I said I'm not going to say much about that, but the idea is this, that one observes that the growth, the rate at which one grows, so Q is the population, or P, perhaps, let me write P here, I guess that is the more common one to use, is P. So P is the population at a given time T, so the variable here is T. Well, very often, of course, in these applications, the variable is not X, but T. So P is the population, and so what we observe is that the rate at which a population grows is proportional to the population, the current population. And that is exactly this. So K is a constant that depends on the type of population you're dealing with. And so this is the differential equation that governs that, okay? That's all the way in the beginning I already discussed it, and this is very easy for us to solve, right? Because we just separate variables. Remember, T is the variable, but it doesn't even appear here. So if you want, this is really the separating the variables. Now you see the variable at T appear here. Now you integrate, we know that is the ln of P, and that is K times T plus C. Of course, there is a constant, integration constant here, to get rid of, to solve for P with exponentiate E ln P, so let me not write that, that's just P, right? And then here we have, let's call this constant here D perhaps, because I'm going to rename it later, E K T plus D, and then we want to split off this constant here because it's just a constant, so I can rename it later, but the real juicy part is in the second part here, where the dependence on T is. So this is, so if we call this C, then our formula for population is CEKT. And C and K, of course, are determined by the situation. C is determined by the initial condition, K is determined by the type of population that we are dealing with. And in part of this, so far I'm saying about population and growth, but there is another application that is exactly the same, because we can think of it as population as well, and that is what is called radioactive decay. And so what does that mean here? Well, decay here, I haven't really said what is K, but there are two possibilities really. K could be bigger than 0, and then we are talking about exponential growth. Why do we say growth? Because as T gets bigger, this function will get bigger. In fact, in the limit it will be infinity. If K is less than 0, then we get e to the negative something T, and as T goes to infinity, that goes e to the negative infinity, that is 0. So this is why decay says. So the limit is totally different. In growth, we have exponential growth, means that eventually your population will be infinite, which is of course not desirable in most cases. And On the other hand, if you are dealing with decay, then in the limit it will be 0. Okay, and so decay, of course, we don't really. Okay, it's why is radioactive decay part of this? What is radioactive decay? What does it come from? Well, we have stable molecules and we have unstable molecules, and the molecules that have. Let me perhaps give an example here. Sorry, let me look up here. Oh no, I'm in the wrong section. Give me a sec here. I'm going to pull up the example. No, here, this example. Okay, here. So, for instance, if we have a substance, a radioactive substance, so these are often isotopes. This means these are not the actual molecules, but molecules that have a bit extra atoms that they that is not the system of atoms and protons is not stable. So at some point that molecule, that isotope, has to lose these extra electrons that it had acquired. And so that is the decay part. In other words, so it's the growth of the population here is in some sense the atoms that are around that make up, or not the electrons. Sorry, the electrons that are part of the atoms of this isotope, and those diminish. So this we have a decay here, and very often this decay is expressed in half-life. So the half-life, for instance, so the half-life of a radioactive substance is, let's say, 1620 years. These half-lives can be very long. Now, what does a half-life means? What does that mean? So here we're going to have Q of T is the amount of these isotopes. So that is the amount of isotopes of radioactive substance, of this substance. Okay, that's Q of T. And what does a half-life mean? That means that after 1620 years, if you started with 100, you're going to have 50 left. So, in other words, as I said, what happens with these isotopes is they lose electrons and then they become inert and they are no longer considered radioactive. And so, as they lose electrons, at what rate do they lose this? Well, this is what half-life is. So this is always in years. So most isotopes are very slow in decaying, which is bad news because where does this come from? These isotopes, they come from in the universe. They come from bombardments of elemental particles, that sun rays and so, that bombard electrons and so. But that is outside our atmosphere. Within us, in our on Earth, most of it comes from us producing them because in nuclear fusion and nuclear reactions and so, no, fusion doesn't exist yet. It's not worked out yet. But nuclear reaction, or nuclear bombs. Unfortunately, we have already seen two being deployed on humans, but there's still the enormous threat of these nuclear weapons, right? But of course, many nuclear weapons have also been tested, and that creates both this nuclear plants create radioactive substances which are dangerous for us. Why are they dangerous? Because these electrons that they emit, remember I said we have this nice, this is how it's supposed to be, and then there are two, let's say, rogue electrons that are not supposed to be there, and they at some point they're gonna have to leave. But what they're doing then, when they leave, well, they have nothing to attach to. They are rogue electrons, and they can damage, when they go through our body to our tissue, they could damage our tissue severely, and to an extent that people will die from this. And I don't know whether you know the history of this, but the first person to actually not die from it, probably other people have died before her, but the first that actually observed this and actually unfortunately died from it is Madame Curie. Yeah, I'm sure you have heard of her. Why was I saying this? Yeah, so, right. And so what is the formula here then? So as I said, one expresses this often in half-life, and the formula for half-life for if you know the half-life, which we sometimes call tau here, then the constant k is equal to ln of 2 divided by that half-life. Let me write half-life here. Okay. So, for instance, in this example, we see that the constant k would be ln of 2 divided by 1620. Okay, let me work that out, what it is for you. Well, perhaps they have done it here in the book, then I don't have to do this. Sorry. Which was the example that I did? Okay, and this. Yeah, they didn't calculate it. So, okay, let me calculate it quickly for you. So it is the ln of 2, where's the ln? Log e, divided by 1620. So that is 4.2 times 10 to the minus 4 in exponential in scientific notation. These are extremely small constant because the half-life, it takes so long, right? And so we know that our solution is of this form here, and then we could ask, okay, so using that but of course it's a negative number, so I should perhaps put here a negative here because we are going, it becomes decaying. It's the opposite of growth, right? So it's the negative of this thing that I should actually write down, and so in this case it would be so the equation that would govern this would be qt equals c times e to the minus 4.2 times 10 to the minus 4t. Okay. And what is c here? Well, c is initial condition. So at time t equals 0, this is the what we call q0 is the value at the starting time, the initial population, the initial concentration, and it's very easy to see if you plug this in here. We can already see it here. P of 0, of course, is just c here. So c is just P of 0 here, the initial population, the amount at time 0. So let me perhaps fill that in here so that we have this right away here, P0, and so here we would have Q0. Okay. So, for instance, if Q0 is 4, one would ask, okay, how much out 8 after 110 years? How much is there left after 110 years? So we plug that into the equation and we work that out. I'm not going to do the details. That is just number crunching. That's not interesting at all. This is more explained in the book. One more thing I would like to say is that in some sense this is perhaps a little bit naive, because as I said, we are also creating it. So a more realistic model would be that the rate at which these radioactive isotopes change is the rate of increase minus the rate of decrease. So this rate of decrease, this is the decaying. This is the radioactive decay. That is where this comes from. What is the rate of increase? Well, that is how it is being made. As I said, it could be from example. So from an example would be from a nuclear plant. Or it could be from cosmic radiation that creates a certain amount of radioactive material on Earth. That it does exist, right? And so often this rate of increase is rather constant, because I mean we have a plant and it's just working, let's say, or we have, for instance, other place. Of course, I should have mentioned is X-rays, right? That's also radioactive material that is used here. So it is a constant. So very often the model would be that's a constant rate. So it's a constant rate. I mean, of course, it doesn't have to be, but in most realistic models, that is a constant rate, whereas the decay is proportional to the population. Not. And so you would have you see here non-homogeneous, right? If I would write it down as an equation, it would be a non-homogeneous but a very simple one. Okay. Now I'm not gonna, as I said, this is not really something. It's old stuff, if you want. But let's talk something new. That is something. Yeah, another thing that you can mimic or model with this thing is so-called compounded interest, continuously compounded interest, which approximates the usual interest that we do. Again, I refer to you. So let me write it. Read more in chapter 4.1. And I will assign perhaps one or two homework problems of it so that you do a little bit of, that you get at least to see it a little bit. But let's go to something a bit more new for us. And so 4.2 is Newton's law, Coulom's law. And so again, it's a kind of same, I mean, once you observe nature, I mean, of course, this is, how do these laws come about? These people observe things and recognize things. And so Newton and his predecessors, because it's not just Newton, obviously, this has been studied from many, this is in the 17th century, but even already in the 11th century in Baghdad or in the Islamic world, in Iran, so they were already studying these things, and it was translated to the medieval Europe only several centuries later, and then it came into what we call the Renaissance and the rational period of European history, science development. But these were all based on observations made by ancients already, or by previous scientists. And so what people recognized was that, so now we're talking about T is temperature, and again we measured in time T, and that could be years, minutes, seconds, it depends a little bit on what you do. And I think in most other things we will measure it, well, we'll come to the units. Yes, another thing. Of course, units in physics, units are very important. We are going to be very sloppy with units. Okay, it's not physics. This is mathematics. Okay, so the temperature. So what happens? What is the situation that we're looking at? We have let's say we heated up an object, like for instance, I just boiled an egg, and now I want it to cool down so that I can eat it. So I put it in a cold water to cool down. And so the question is, how long does it take for the egg to get colder? Okay. Now, if you do it with an egg in a little bit of water, what happens, of course, is that the egg will cool down, but the water will warm up a little bit because the heat distributes into the water. If I put the egg in, let's say, in a lake to cool down, the lake is not going to warm up because of the the one egg or that I put in there. So very often, so we have an object. So the temperature that we measure is of that object, and we put it in a medium, and that medium has a certain temperature that I'm going to call Tm, but that is assumed to be constant. In other words, not affected by whatever I put in there. So we always have to therefore think, you put something hot in a huge bath of water, or you put something hot in a cool room, a big room, and so that the small object, what the effect of that small object on the temperature of the large environment, the large medium, is negligible, and so we consider it just constant. And what then? So of course, in the beginning, there is a difference in temperature. Okay, and we also have the rate at which the object changes temperature, and strangely enough, what seems to happen again, this is constant, proportional. Sorry, it's proportional. So the rate at which something cools down is proportional to the difference of temperature, right? So, and it kind of makes sense, right? If you put a boiled egg in lukewarm water, it will cool down less than if you put it down in, say, an ice bath. So the more the temperature, the bigger the difference of the temperature, the faster or the more it contributes to the cooling down. Now there's also a cooling down constant that depends on the medium. Okay, this K depends on the medium, so there should be perhaps a little m here. Now, and it's cooling down, so it is custom to think of K as a positive number and write with a negative here. So the negative means the cooling down. Now, in this model, of course, you can go other way around, right? You could put a snowball in a room and watch it melt, and it's basically the same thing. It's not cooling down, it's warming up. So cooling, it's normally called cooling because that's what's the most observable, but in some sense it's the same as warming, except then we would have a positive constant, okay? But let's concentrate on cooling. So, okay, this is the model. So let's write down what this mean here. So if I factor this out, it's minus kt plus ktm. So I'm going to put this here, bring this to the other side. The ones that t, remember t is now the variable, the function, right? And little t, so capital T is the function, little t is the variable. So, and this t is perhaps misleading. You might think, oh, this is also a variable. No, Tm is, as I said, constant. Okay, so I just keep the notation of the book. I would have used a different letter because otherwise it's a bit confusing here. Okay, if you want, let me call it a tau, which is almost the same as a t, but at least it's different. Now you don't. Now tau m is just a constant. So what is this then for an equation? So this is a linear equation, right? But not homogeneous, because there's this part here. Now again, this is very easy to solve. Let's just do it. Let's do it on an example rather than do it in concrete here. So suppose we have we bake an insulator in ceramic. So we put it in a baking oven. It's cooked, and so its initial temperature. Okay, what is that? That would be T0, right? Remember, T is the temperature of an object, and the initial temperature is 400 degrees Celsius. Okay, let's just work everything in centigrades. And it's cooled in a room, so the room is 25 degrees. A big room, so this is what my tau m was, the medium, the temperature of the medium was tau m. And we don't know K, but we can make observation. We know that this is the model, and say that after 4 minutes, T, so T4 in other words, is equal to, it's cooled down to 200 degrees. So rather rapidly has cooled down. And that's not surprising, right? Because the temperature difference is quite high, 425. So this is going to lose a lot of radiation, a lot of heat is going to come off it very quickly because of the room. So the question, so this is the situation. Let me read the actual question. A ceramic insulator is baked at 400 degrees, that's the T0, and cooled in a room with a temperature of 25 degrees, so that's the tau m. After 4 minutes, the temperature of the insulator is 200 degrees. What is the temperature after 8 minutes? What is T8? Okay, so how do we set this up? Well, we know that this is our equation, but the one thing we don't know yet is K. Okay, so we have to first solve this differential equation in general, but that's very easy. Remember, we do this minus kt, then t prime over t is k, separating variables. The little t is a variable, it's not there, but okay, if we do it this way, we see it. It seems like we're always solving the same differential equation, right? Oh, sorry, no, I made a mistake here. Let me write it again. D capital T equals minus k dt. It's always the same. It's the same as the exponential growth equation that we are doing here. At least what I mean to say here. Sorry, ln of t. The complementary equation, the homogeneous part is the same, and this is e to the minus. Sorry, I'm going too fast. ln t is minus kt plus a constant. So t is e to the minus kt plus d. That is e to the d e minus kt. That is c times e to the minus kt. If t is 0, then we see that we get c. So our solution is t is equal to t0 e to the minus kt. That is the homogeneous solution. So I should write that the homogeneous solution. Okay. Oh, sorry. Yeah, sorry. I should not have put t0 equals 0 here. No, let's not go too fast here. So this is our homogeneous solution, but that's not what we want. But we want a particular solution. And how do we do that? Remember, you take this is, so let me call it T homogeneous. Okay, the H and P are now just temporarily. I'm making distinction between homogeneous and the actual solution. So remember, this is the formula that we use then to find a particular solution. So we know that T, I'm now going to write T again, is U times e to the minus kt. I can take c whatever I want and I take c equals to 1. So T prime is U prime e minus kt plus U times minus k e to the minus kt. Product rule. Okay, minus k from chain rule. So we plug this into the equation. We have T prime plus kt equals, what was it? Plus ktm. Plus k tau m, k tau m. So if I plug this in, what we get, U prime e minus kt plus minus, let's put the minus there, minus ku e minus kt. So this is this part that I have, that's the T prime. Now I have to do k times t. So plus k times t, which is this one, u e minus kt equals k tau m. We know that certain things have to cancel, which luckily they do, and we have a separated variables. U prime equals k tau m e to the kt. I'm bringing this guy over to the other side by changing the sign of the exponent. That's one valid reason to do. We know that this is a separated variable, so if I want to do this, and it's good to write it this way, because now you see what is variable and what is constant. So k and tau m are constants here, right? That's also something we always have to keep in mind. So we get k tau m, and then the end derivative of akt is e to the kt divided by k. Remember, this is the end derivative of e5t is e to the 5t divided by 5, because but if you take derivatives you get an extra 5 from the chain rule and want to cancel it out. So this is what happens here. This of course is u. We're looking for a particular solution, so the k's cancel. We see that u is equal to tau m e to the kt. So what is our solution, a particular solution now? The particular is given by this formula here, right? Is this one? It's this one here. So it is u is tau m e kt times e minus kt, which is just tau m. It seems like a lot of calculations to get to a simple thing, right? And that's why we not always do this, and we have formulas. Of course, we don't always work out the differential equations when you do this cooling. So what does this mean? So the particular solution is tau m. Now remember, the general solution is the homogeneous solution, the general homogeneous solution plus the particular solution. The general homogeneous solution, that was, where did I write it down here? Let me box it. That is the general, oh here, yeah, right, this thing, right? That's the general homogeneous solution, and the particular solution, so let me write that up first. So that is c e to the minus k, e minus kt, plus the particular solution was just tau m. Okay, so let me write it down now without the subscripts anymore. So when sometimes I hope you don't get too much confused by that. When I use these subscripts, it's temporarily to tell me it's a different type version of t that I'm looking at this particular calculation. But in the end, it's the actual t that I want to calculate, and so we find that this is the general solution of the cooling equation. Okay, so we actually solved the cooling equation in general. We now gonna use the data that we have. Let's see. Well, first of all, what we know. What was the data here? T0 is, so we know that if t is 0, then capital T was 400. Let's start with that. 400 equals C times 1 plus tau m. Okay. That's a bit, you say, oh, that's bad because I don't know what tau m is yet. Okay, but we have more. at T equals 4, we know that the medium, we measured the temperature of the object, of that ceramic insulator, was 200. So that's 200. So let's see, at 200, we have, if T is 4, so T is 4, so now we have C e to the minus 4T plus tau m. So we now have to try to find, so we get a linear system of equations, right? With two equations involving two unknowns, C and tau m. So one way is substitution. You solve for one and substitute in the other. Another one is, for instance, cancellation. Like for instance, if I see here, if I take this one and subtract this one from it, what do I get? Well, 200 here. Here, if I subtract, I get C minus C e to the minus 4k 4t, and then the tau m plus tau m minus tau m, they cancel here by subtracting, right? So this is what I find, and so we see that 200 is C times 1 minus e to the minus 4t, whatever, sorry. 4k, right? Sorry. Yeah, the t is 4, yeah, 4k. And so we have minus 4k here. Okay. Okay. Oh, yes. Sorry. We know what the medium was. Sorry, I said there was an unknown. No, we know that, right? I forgot to put that in here. This was given here. Tau m is 25. So now I've used everything. Sorry. So this is actually, sorry, I was solving the wrong thing. Well, I was solving for the wrong thing. Let me put it like that. So these two equations are correct, but let's write them out more correctly. What I have, 400 is C plus 25, sorry, we know what tau m is, so we know that C is 375. And so from this equation then, we 200 is 375 e to the minus 4k plus 25, okay? But tau m is 25, right? So we see that 175 equals 375 e to the minus 4k. So we see that 175 divided by 375 is e minus 4k. So we say that minus 4k is equal to the ln of 175 divided by 375. And so k is equal to minus 1/4 ln 175 over 375. And let's see, I think they calculated this for us. No, they didn't. Okay. Okay, so that number, let me calculate it for you. I hope my calculator. I never trust my calculator because I have to do this on a very rudimentary iPad kind of thing, and so no, sorry. Let's clear everything here. Okay, I do 175 divided by 375. Okay, now I take the ln of this thing. Let's log that. Okay, and divide by 4, and I get this is to be 0.190. I'm going to round it down to 0.2. Okay, so the question now, remember what was the question? What happens at time 8? Okay, so we have, let's write down what we know. We have our equation here, but we know a little bit more now. We know that C is 375. Do we know K? Yeah, we know that K is 0.2 here, so minus 0.2t, plus, and tau, we know also what tau m is as 25. Okay, so now we have to just plug in t equals 8, so that would be, so we have 1.6. Well, let me not work that out. I know the outcome here. They told me that this is going to be, if you work this out here, so what we now know, sorry, let me write that. Okay, let me write that. So T8, that is going to be 375 e to the minus 0.2 times 8 plus 25. And if you calculate that number. It's supposedly to be 107 degrees. Okay. So after 8 minutes, it's getting there, but it's still hot. So you could ask, how long will it take to become actually 25 degrees? Well, if you look at this equation here, what happens in the limit? Let's take the limit for t going to infinity of this equation. What happens if at t infinity, so this goes to infinity, so this, because it's negative, goes to negative infinity, e to the negative infinity goes to 0. So in infinity, this term is gone, and we have 25. So in principle, it takes infinite time to actually get to the room temperature. Now, obviously, that's not really what we observe, is because, I mean, for us practically, how long will it take before we get around to 25? Let's say 26. When it's at 26 degrees, you could try to solve that, right? In fact, it's not so hard, right? Let's say, when is it 26 degrees? So I'm doing an extra question. So when is it 26 degrees? 26 is equal to 375 e to the minus 0.t plus 25. So 1 is equal to 375 e to the minus 0.2t. Let's bring the 375 to the other side. Okay, I do that magically by erasing it like that. And so now we see that if I take ln of both sides, so the ln of 1 over 375 is equal to minus 0.2t. So how long will it take? T is equal going to be, that is minus 2, that is minus 1/5, right? So 5 times, minus 5 times ln 1 over 375. Multiply both sides with negative 5. That's how I get to this equation. You know, right? Minus 5 times 0.2 is 1, right? Okay. So what is this? Let me just do that. So we have 1 divided by 375. Now we take the ln of that thing and we multiply that with 5, and it's and take a negative of that. So this apparently is about 27. So it will take about 27 minutes. Was it? I think we were measuring things in minutes. I don't even know whether I said what the units were. Yeah, minutes. So after 27 minutes, it will be almost cooled down completely. So we'll be almost at room temperature. Okay? So that's not that long. It takes, that's kind of funny, right? It takes only 27 minutes to get to 26 degrees, but from 26 to 25 degrees takes infinite long. No, that is how, when mathematics is exact, and physics of course says, no, come on guys, that's not the case. It goes quicker, right? Because it's almost equal. Remember, we did make one assumption, which is technically also not correct, is that the medium did not change temperature. There would be a minuscule change in temperature because of that, but all right. Okay, that is cooling. There is one other thing, that is mixing. So how does that go? The mixing problem. So in mixing, we have a certain, again, Qt is a solution, and it could be other things, but let's focus on saltwater solution. I don't know why the book only discusses saltwater, which seems like, why would you make salt water, right? But okay, that seems to be what they're doing. So a saltwater solution. I wanted to do two problems, but I don't want to make this video too long, so I'm going to do on one problem. Sometime to think, what should I do here? I'll take the longer problem, a little bit more problem. So let me read this, but I'm going to change it slightly. So this is example 424 from the book, but I'm going to simplify it a little bit. So I'm reading the question. A 500-liter tank, and that is the part that I'm going to ignore. I'm going to say a huge tank. I'm not concerned how big it is. So a tank initially contains 10 grams of salt in 200 liters of water. So that is the amount of salt and the amount of water that's put, and we constantly stir, so it's always equally divided. Now, when t is 0, so at the beginning, we well, that doesn't make here, forget about that part, because again, that's not important. We add, So somebody is standing there with a spoon and adding 1/4 gram of salt per liter. Sorry, no, he's not adding. Sorry, he's not adding salt. He's pouring water that is a salt water mixture. So this is a mixture, so that has 1 gram of salt per liter, and he pours this. It's added at a rate of 4 milliliters per minute. Okay. So what? In other words, here is our tank. Okay, we have some water in the tank. Now, what we pour in water here that consists, it's not pure water, we put in water that contains salt, and the concentration is 1/4 of a gram per liter, and we pour that at a rate of 4 liters per minute. So every minute 4 liters of this type of solution is being poured into the tank. But of course the tank also, we want to, supposedly we are using this mixture for some purposes, so we also taking away here. And so this is at 4 liters per minute, and it is being emptied at 2 liters per minute. And emptied at 2 liters per minute. Okay, and so we would like to have a function of T. This is the Q of T is gonna be the grams of salt per liter in the tank. So it's a concentration. In other words, it's the concentration of salt per liter water in the tank. Why is that changing? Well, there was a certain solution. There was a certain solution of 200 liter, and it was 10 grams of salt. So let's say, what was Q0? Let's start with that. Well, we had 200 liter, and that was the concentration. That was 10 grams of salt. I'm sorry. Let me figure out here just that I have. Yeah. Okay. So 200. No, sorry. The concentration is grams per liter. I said so. Sorry. That's what I was trying to check. It's grams per liter, right? So the salt. It's how much salt we have. We had 10 grams of salt, and we had 200 liters. So this is grams per liter. I have to make sure that my numbers fit the units. That they all. A tricky problem is a problem where the units don't match. I don't like that. So I'm going to pretend that all the units are matching all the time, right? Everything, if we use grams for one thing, we use grams for every other thing. If we use liter for one thing, we use liter for everything, and not gallons and not other concentrations. So this is the original solution, the original solution, which is 1/20, 1/20th, right? If we now ignoring units, I'm not going to write units anymore. But we're adding, notice what we're adding. We're adding something that has a higher concentration. There is 1/4 instead of 1/20. So in other words, as we pour in this water, the solution in here, so the water in here will become more and more salty. Okay? And so the question now is, what is the salt content at any time? Okay, let's try to write down what we have here. So what governs this differential equation? What is the differential equation here? That's, of course, the more thing. Let's put it out. Well, there are two things. There's the rate. What is the rate at which this concentration changes? There's the rate of influx minus the rate of outflow. Perhaps let me inflow and outflow. Let me write it that way. Of this concentration. Okay, so we have to determine both. What is the rate of inflow here? Now remember, we have the concentration of the solution that we pour in is 1/4, right? 1/4 grams per minute. But pouring it in at a rate of 4 times 4 liter per minute. So it's 1/4 times 4, correct? So it is 1 gram per minute that of concentration that will go in. What is the rate of outflow? That is a little bit more tricky. So what is the rate of outflow? We can say it's the concentration times the rate of the outflow. Of the water flow. So what is this? What's the concentration here? So what is the concentration? Well, we need to know actually how much water is in the tank. So let WT is the amount of water. Okay? Because the concentration, to know the concentration, you need to know how much salt there is. That's Q. Q is an amount of salt, right? And, oh, sorry, wait, okay. I think I made one mistake, and that's why I was keep checking it. And the quantity of salt, so sorry. QT is the amount of salt, sorry. Amount of salt. Okay, not the concentration, but the amount of salt. So the initial condition was, I was wrong, right? I said this was the rate, that was the concentration. No, the initial condition was just 10. The amount of salt was 10 grams in the water. So we at any time we measuring how much salt do we have in that thing. But of course that doesn't tell us that there's also more water coming in. So we also have to, in other words, there are two things that change in the whole thing: the amount of water and the amount of salt. So let's first think about the amount of water, because that's not so hard. Okay, let's see. It started with 200, right? That's at time 0 there were 200, right? 200 liters. Now at any minute we add 4, at the rate of 4, so 4t at time t. So the rate after time t times will be 4t added, but we also drain at the rate of 2. So we see that the amount of water at time t is given by this formula. I hope you understand what it is. Constant rate 4 means that after t time there will be 4t water added, but we also subtract 2t water. So at any time we have added 2t water, the amount of water will be 2t more, and we started with 200. So that is that. Okay, so now, so here is how much salt was coming in, right? We had 1/4 gram per liter, and we added 4 liters. So there's 4 times that, so that was 1 gram of salt was getting in. How much salt I was getting in here? So what we can say is, well, it is the concentration of salt. So here I'm going to now talk about the concentration times the rate of water loss. Okay? The concentration of salt per water times how much water we pour out. That will be how much salt goes out. So this is the rate of inflow of salt. This is the rate of outflow of salt. Okay? So the concentration, what is the concentration? Well, the concentration is the amount of salt, Qt, divided by the amount of water, right? Concentration is salt over the amount of salt over the amount of water. Now the amount of water is given by this formula, 200 plus 2t. What is the rate of water loss? Well, that is this rate 2. Okay? So that's where this formula comes from. Okay, and we can perhaps even cancel the 2's here in the denominator. That is Qt. If you cancel a 2 in the denominators, every term has to be divided by 2, right? So we get this. So what is our differential equation? Q prime equals 1 minus Qt over 100 plus t. So you might have thought this is going to be a simple problem, but you see it's actually not so simple problem, because you get a really differential equation here, a true differential equation that we need time to solve, which you couldn't do with just calculus. So this is why this water comes in and water comes out. Yes, that is something you learn in pre-calculus, but now with salt being added to it, so now we're talking about solutions, that is much trickier. And that is kind of already surprising, right? It seems like a simple thing. You're just pouring in some water and you draining some water, you put some salt in there, what a big deal. But you see the equation is not as trivial as you might think it is. Okay, so let's solve this equation. So sometimes when I solve an equation, I get confused by the letters. So if you want, you can write it in just using your y instead of t. If the q's throw you off and this q is a constant, or this q now, or get lost, this q is what? So if you do it that way, I keep t as a variable here. Now you see that this is a linear equation, but non-homogeneous. So step one is the homogeneous part, the complementary homogeneous equation. So we need to solve this, we want the general solution for this. So we have y prime equals minus y over 100 plus t. There's separation of variables, right? That is dy over y equals minus dt over 100 plus t. Did you follow what I did? Yeah. Okay. So and the deriving, this is ln of y equals minus ln of 100 plus t plus a constant. We need a general solution eventually. And so if I want to get rid of this, I take the exponentiation, that is y equals, let me put this d here, because I'm going to change it again, e minus ln 100 plus t plus d, which is e to the t times e minus ln 100 plus t, that is just 1 over 100 plus t. Okay, so this is c over 100 plus t. That is my solution. So writing it with the q homogeneous, the general solution is c over 100 plus t. Okay, that's our solution. So what is now the particular solution? Let me write y again. Since I'm doing calculations, I'll write the y. Remember, that's the formula for getting setting it up. And so this means here that y is equal to u times, I can take c equal to 1 now. So I'm going to take 1, because it's a particular solution. Now, it doesn't matter what c, I can take one c that I want. Of course, I take the easiest one. I have to do, take derivative of this thing, that is quotient rule. I don't like quotient rule, I'm doing the product rule. So u prime times 1 over 100 plus t, plus the derivative, copy u, take the derivative of that guy, which is, this is just 100 plus t to the power negative 1, right? So that is negative 1, 100 plus t to the power negative 2, or if you put this all. So let's now plug this into our differential equation here, this one, or this one, let's put it in this one. So y prime is this guy, u prime over 100 plus t, minus u over 100 plus t squared. You with me? Okay, that's now we have y over plus y over 100 plus t. But what was y? Y was c. This was one. This was y, right? This one. So this is actually u 100 plus t equals, and that whole thing was just equal to 1. Okay. Now you see that what we get here, this is a 1, sorry, let me point. This came from here. Yeah, just let me mark it in case you got a little bit lost from where everything came from. So this is y, right? So this is why I had a y here. Okay, the rest was part of the, and this was y prime. So this goes here. I mean, yeah, this whole thing is y prime. Okay, this is y prime, this is y, and that was equal to 1. Now we have 1 over 100 plus t here and 100 plus t there. Together this is 100 of t squared in the denominator. This is exactly this term except for the sign. So these two terms cancel out. That's my whole point here. So we find, and this has to happen, we don't know that, we find u prime equals 100 plus t equals 1. So separating variables, du is equal to 100 plus t dt. And now we can integrate. U is equal to 100 t plus t squared over 2 plus a constant, but we don't need that. And so that's what we have. Okay. Yeah, you could also, what the book says is, oh, it is this they say. Now, if you work this out, you might say, no, that's not true, that's different. This thing is different from this thing, and you're right. But what's the difference is a constant, and so we only need to take one of them. So you can take this form, which is a little bit more compact, or you can take this form, which is what you would just normally do. Remember, when we take a particular solution, we can take C whatever we want. So what would the C be here, by the way? If you would expand this, you will figure out that C is actually 100 squared divided by 2, 5,000, yes. So the C here, the difference between the two is a 5,000. So where you would say, oh, let's take the simplest constant, t equals 0. If you would take C to be 5,000 here, so normally it's a constant of integration here, then you get this form, and it's in an easier, neater form. It's not important, so I'm gonna, let's take the more naive approach, and so let's write down what we have now. The general solution is y equals homogeneous plus this particular solution, so let's write it down in q's now. Q is equal, the homogeneous solution was C over 100 plus t, and the particular solution that we got was, be careful, this is u, right? We still have to multiply this with y, so it's this form here. So this we see now, the particular solution is u, which was 100. So you see here, okay, no, I chicken out. I'm going to use this form because it's so much easier now, right? Because now I get these nice cancellations here. Otherwise you wouldn't see this cancellation, and it's not true. It doesn't cancel because, but it's just, the difference is only constant, which is something that is anyway encapsulated in our setup. So so in other words, if we do this way, we see, oh, sorry, not 100 plus t over 2. This is the homogeneous, so the particular solution. Okay, using, as I repeat, I use this form, which means that I use a constant of 5,000 here. But you don't have to take that constant. You can just do integration. You say, okay, sort kind of substitution, right? If you do substitution on this thing and integrate, that's what you get, plus a constant. Okay, and here I take the constant 0. If I do it just term by term, I take the constant 5,000. So this it's a small little thing, but it shows you that sometimes it's not always advantageous to take the constant to be 0, even if it doesn't matter. Okay, so going back here. So this is our solution now. This was the particular solution, this is the homogeneous, the general solution. Now we have to use something still. We know that Q0, what would that be? That would be C over 100 plus 100 over 2, that's 50. Right? If I plug in, so here t equals 0, what was q? Well, we said that, right? Q was, I made an originally mistake, but it was 10. It's the amount of salt originally into the that we started with. So that was 10. So we see that minus 40 is C over 100. So we see that C is minus 4,000. Sorry, I just want to see here. Yeah, I think it's the same thing. Yeah, okay. So we have, whereas I got a little bit lost now. Where's my here? Yeah. So Q of t at any time t is minus 4,100 plus t plus 100 plus t divided by 2. Okay. Yes, that's the formula. Okay, and now we could ask, what is the concentration at any time, and what would be the concentration be? Remember, the concentration was the amount of salt divided by the amount of water, and we know the amount of water was given by this formula. So from this we can also find the concentration. But so and I think, I haven't checked it, but I think if you try to write down the differential equation for the concentration, you get a much more difficult one. So it was advantageous to try to find the amount of salt, write the differential equation for that, and then solve. Okay, this was still a bit long perhaps. I'm going to do some homeworks on this, and then we will have a video on the next thing on mechanics, another application of first order linear equations. No, first order equations, not necessarily linear.